theoretical probabilities of simple events. So this is going to kind of lay the foundation for probabilities for us, and we're going to move forward into compound events and kind of make this a bit more complex, but this will be good information from this for us to have at the beginning here so we can move forward in this concept of probabilities. So start with this little word problem. At a school fair, you have a choice of spinning spinner A or spinner B. You win an MP3 player if the spinner lands on a section with a star in it. Which spinner should you choose if you want a better chance of winning? Got spinner A, spinner B. So our probabilities here, which one's going to give us the most likely outcome of us winning this MP3 player? Well, these are different kinds of spinners, though, obviously. They have different number of spaces to land on, the sizes are different, and they have a different number of stars. So which one actually gives us the better chance of winning this MP3 player? So I give us a little extra space here. So the first thing we want to do, we'll start with spinner A right over here. And first thing we want to know is, what's the total number of spaces we could actually land on? We flick this spinner, anything could happen, but what are the total number, basically, of like pie pieces that we could land on? And if you count them all up here, we should have 8. So that kind of acts as our denominator and helps us figure out our basic probability here. Now, how many have stars? Not too bad. We have 3 of them with stars here. Okay, well, to develop the probabilities, our theoretical probability, you can write a probability 3 ways. You could write it as a fraction. Basically, we have a 3 out of 8 chance here. You could actually write this as a decimal too, and that helps a lot of times when you compare them. So 3/8 converts into 375 thousandths, or 0.375. And then you can also write that as a percent. And remember, we can just move the decimal point 2 places over and make this 37.5%. So when you compare them, it's actually easier to do it with a decimal and a percent. So we've done that with spinner A. Let's try spinner B. So spinner B, got to count up all these smaller places. It doesn't have 8. It has more than that. If you count up all of these places, they're kind of tiny. Got to look closely. It actually has double the amount of landing spaces. It has 16. And it has 5 stars that we could land on. So you basically have a 5 out of 16 chance of landing on a star here and winning that MP3 player. So now we need to compare these. We can compare the fractions. You could butterfly these and figure out what the largest is, or you can turn it also into a decimal. So if you take 5/16, you turn it into a decimal. Remember, you just divide the numerator by the denominator. I'm not going to do the division right here, but if you do it, you'll get 0.3125 and as a decimal, and then when you convert that into a percent, 2 spaces to the right makes this 31.25%. So now we can compare which one gives us the higher percent chance, the greatest probability of winning this MP3 player. Well, if you look, it's this one right over here. This is a little bit larger, have a little bit better chance if we spin spinner A of winning the MP3 player. So this gives us a theoretical probability. This is a simple event. This is just one thing we're doing, hitting a spinner, and compound event is if we did multiple things. This is just one as we go through. So theoretical probability is the probability that an event occurs when all of the outcomes of the experiment are equally likely. So make sure you write that down. Equally likely means that when we hit the spinner, we could land on any one of these spaces here. Doesn't matter. We hit the spinner, could land on a star, could land on not a star, a blue, but it's equally likely we could land on any of them. So what is the probability that the event can occur? The event is what we want to happen. We want it to land on a star. So there's basically like a formula that you can use, and it's just like I set it up there. The event was us landing on the star. And if we took A, the number of ways the event can occur, well, how many stars were there? In A, there were 3. So that was the number of ways that we could land on that. And the total number of equally likely outcomes, well, there were 8 of those different spaces we could have landed on. So basically set it up as a fraction, numerator, denominator. And then you can always write it as a decimal and then as a percent to figure out the best probability. All right, let's try this one real quick, and this is pretty quick. You roll a number cube one time. What is the probability that you roll a 3 or a 4? Write your answer in simplest form. A couple things here. A number cube, same thing as a die or dice. You're never going to see in word problems, they're not going to use dice. They're also not going to use quarters. They'll say flipped, like a fair-sided coin, something like that. They won't say quarters, they won't say dice. I think it has something to do with gambling, and they don't like to have that connotation there. But just know that a fair-sided cube is dice, or number cube is dice, fair-sided coin is a quarter, just so you don't get those confused. So if you, on this one, what's the probability that you roll a 3 or a 4? Write your answer. Well, let's think about this real quick. We need the total number. How many different spaces can we land on for one die? A die has 6 sides, so it's like the total number of sections. So if we know that, we know that a die has 6 of them. And then how many are 3 or 4? Well, we just need 3 or 4 here, and that's 2 of them. So you simplify 2 over 3. You could turn it into a decimal percent, but essentially we have a 1/3 chance of landing on a 2, 3, or 4. When we kind of roll this dice or this number cube. So how is the sample space of an event related to the formula? Well, it's related in that the denominator is the same as the total number of outcomes. So 6, the denominator is the same. Denominator, didn't write that very nicely, but is the same as the total number of outcomes, which means we roll this dice, there's a fair chance that it could land on 1 through 6, we don't know, and that kind of sets up our denominator. Last 2 examples real quick, very quick. A spinner has 11 equal side sections marked 1 through 11. Find the probability. A lot of questions that are like this. This is still a simple event. I would real quick just kind of make kind of a very quick, it's not going to be very good, but a real quick spinner. 11 sides is kind of tricky because usually they give you an even-sided spinner. 9, 10. So let's say here's our 11-sided spinner. Here's our center right over here. And we're to assume that these are even sides. You have the same chance of landing into each space. One of them is not bigger than the other one. So this is our not too awesome, but pretty awesome spinner. 11-sided. Thank you very much. So what are the chances? Find the probability to land on an odd. You spin once and land on an odd number. What's the probability of landing on an odd if we hit the spinner? Well, I don't know. How many odds are there? 1 is an odd, 3, 5, 7, 9, and 11. How many odds are there? 1, 2, 3, 4, 5. There are 6. And how many total places could we land? Well, there's 11 because there's 11 spaces. So 6 out of 11, the probability is a 6 out of 11 chance, or 6 11s, that we could land on an odd number. Alright, so also, what's the probability of landing on an even number? There's still 11 equal sides, so I'm going to put 11 there. How many evens did we have? Well, probably 5, because 1, 2, 3, 4, 5. So that gives us a 5 out of 11 chance of landing on an even. So it's more probable that we'll land on an odd here. So this is theoretical probabilities of a simple event, and we'll soon be moving forward into compound events.